All right. So the first topics is the sources of error. Okay, this is one of the essential part in numerical method as well as in the mathematical methods. Okay, so sources of error, there is a plenty of errors in. So we only can cover the first part out of it. The rest part we cover in upcoming weeks. Okay, so yeah, let's move on. Okay, all right. Just anything, you have any guess what the contents we're going to learn today in DIPA? All right, take a look on this video. Okay, now, so what do you see in this video and what you can conclude from this video? Anybody? Hello?
Doctor, I think maybe it's relate to our topic for today about the accident, the
The
error,
accident.
the error,
Okay.
something error in
All
calculation.
right. Anybody? Any other guess?
Doctor, I want to try.
Yep, sure.
Can you hear me? So I think rocket
I do.
science is a very complex thing that it requires both engineering as well as mathematics, and a little errors, like for example the metal, the contract coefficient, like error in those kind of little things, details can result in a catastrophe.
All right, good. All right. So as you can see here, this is a rocket science. Rocket science is not that easy to just like we carry out, because like this is like something like you have to ponder about the systems, calculations, and everything has to be more accurate and is precisely at least like number of the significant errors, significant accuracies is requirements is. So now in that situations, like what happened, this is like just some sort of like mathematical error is just made in this rocket launch. So that is causes the loss of like $1 billion projects. Just go like that, all right? So then you have to think like how the error is important. So always remember, in every situation and every the projects or the calculation that you carry out, the error is one of the significant figures or significant subjects to have to think about, all right, how to minimize the error. Okay, so this is the best example for you, just in terms of reduce your time. Your time is very valuable, as I said earlier. So you can reduce the cost and is you make that the better life. So then you have to think about, how you need to solve this type of the errors. So before you just to carry out, so the error analysis is one of the essential in order to or make sure that the project or any such things, the projects that you carry out is not any mistakes. All right. So yeah, so the error analysis is one of the important parts. So this is what we're going to discuss today. So there is like plenty of errors we're going to discuss, all right, in all these topics, and some of them will be today. We will check what of those type of the error and how we just carry out and tackle those problems. Okay, so first we're going to learn about the true error. So what does it mean, the true error? And then we're going to study about that, the relative true error, approximate error, a relative approximate error, and then absolute error, and then round-off error, truncation error, modeling error, instrumental and machine error, human error, of course, is very common, is everybody like you just going through this, data propagation error, and yeah, so I think yeah, there is like there are a few more, but I don't include because it's like very advanced. So this is like a very basic, the error that you should have to consider when it comes to the numerical methods. Okay, so this is essential in order to you get a better result and more accurate solutions. All right, so this is only the type of the error we have to look into that in numerical approximations. Okay, now why the error is essential? As I said earlier, to determine the accuracy of the numerical result, and as well to develop the stopping criteria for iterative algorithm. So the error is one of the important part. It works on when we just calculate a solution or calculate or solve the problems using the numerical methods. So when you run the programming works, okay, when you write the coding on that your C or MATLAB or ANSYS or whatever it is. So when you just write programming, so you must mention that stopping criteria. So usually the stopping criteria we use in our research level is a 10 power of minus 10. So that is a stopping criteria we usually use. So when the calculation is meet that the stopping criteria, so the iteration will be stopped and then it will be give the solution. So that is the technical part, which is we impose, we carry out in the numerical analysis. Okay, so in the future, I mean, like in upcoming weeks, we going through some of the subjects, the numerical method, and I will tell you and I'll teach you like further how to calculate all those kind of methods. Okay, no worries. So for now today, you just only look into that the errors, and then you need to know how to calculate those of the errors. Okay, so these are some of the learning outcomes. So yeah, so you'll be able to do all this after once you just done these chapters. Okay, all right, the first things, the true error. So what does it mean, the true error? The true errors is defined as the difference between the true value and calculations and the approximation value found using the numerical method. Okay, so usually we just consider in order to find the true error. So what we need to know the true value and then the approximations value. So this two is important, right? True and approximation value. Okay, so true error can be calculated. So usually they will be denoted with that capital A, with the T is stand for the true value and equal to, so true value minus that approximate value. So this is your first equation you're going to learn in this chapter. Okay, all right. Now, usually when we just look into that approximation function or approximation formula, so this is one of them. So it derived from that finite difference equation. All right. So it is also be called as the first order forward difference formula. Okay, this is a first order forward difference formula. So we also be used as a approximation function. Okay, so let me calculate the true error. So based on that, the given approximation function. All right. So say the given function is fx equal to 7 exponential 0.5x, and this h is stand for the step size. Okay, so this is your step size. Okay, so step size. So say this is your equation. What does it mean step size? So we can see quickly on there. So this is your graph. So say you're going to calculate that the function of this graph between A to B, say A to B. So, and you just make that the partitions between the two boundaries. All right. So this is, we call the step size. This is we call value of H. Okay. So also be remember that as much that H value is lesser, the accuracy solution will be higher. Okay. So this is like a concept you should understand. Okay. Now we're going to calculate the true error of the true error is calculated, you know, based on the given function with the step size. So first we're going to determine the true value of this function, and then after that we're going to calculate that the approximate value of this function, and then we calculate the true error. Okay. So I just do some demo how we're going to find out this. All right. Okay, take a look at this example. All right. So first we're going to do that find out that the true value. Okay. So true value, as we know that the function is given, which is based on that function. Hang on, just and because of white color. Okay. So first we're going to look for the true value. So true value, you just use the standard derivative, you know, concept. So when how you're going to do the derivative, and you know, so this is fx, as we know that 7 exponential 0.5 x. So as usual, you do that the first derivative functions. When you differentiate this function, you get 3.5 and exponent to 0.5x. Okay. Now, if you just substitute the value, so when the first order derivative, when the x is 2, so you get 3.5 exponent 0.5, and this is 2, the x value, substitute there, and you get how much? So you get you just calculate and you get a 9.513,986. All right, so just leave your answers at least 5 decimal places. Okay, so that you can see that the accuracy and so on. So, all right, now next, you already find the true value. Okay, true value already find out. Okay, now we're going to find out that the approximate value. Okay, approximate value. So how are you going to find out the approximate value? Is very simple, as we know that the approximation function, which is the first order forward difference formula. So as we know, this is like fx equal to fx plus h minus fx and over h. The h, as we know, is step size, and we know the function, which is that fx plus h. The x, we know that this is f, this is x is, we know this is 2, okay, and the h is already given the 0.3, okay, and then fx is 2, okay, and then the h given, which is 0.3, Now we just substitute with the function. All right. The function, as we know, okay, this also can be written as this. So this is f 2.3 minus f2 over 0.3. Okay. And now we just plug those value into this function. So, okay. So what is the value is? So this will be give you roughly 10.264.592. Okay. All right. So now, so once you just get the solution, so you're going to find that the approximation function. Okay, the approximation error. Okay, the true error, sorry, true error. So true, as we know that the formula is a approximate error minus your true value minus with that approximate value. Okay, as we just studied just now, the formula based on the formula. Okay, oh sorry, is that up there? Okay, true value minus approximate value. Okay, so we're going to calculate over here. So we know that the true value is a 9.513986 and minus 10.264592. Okay, so there's a difference is that will be the result. Okay. So that should be a minus 0.750606. Okay. All right. So this is the true error between the true value and the value. Okay. So remember that. Any question, guys? Is it clear?
Yes.
Yes, Dr. Clear.
Okay. Oh yeah, the class is recording now. All right, don't worry about that. So I will post out in the channel later. Okay. All right. Next, relative true error. Okay, relative true error is the ratio of that absolute error to the true error. So usually in the numerical mathematical methods, the relative true error is one of the essential as well. So always look into that in the ratio. And this ratio usually will be expressed in terms of percentage. Okay, that is a very common in practice. Okay, so the relative true errors equivalent to that the element of the t. So usually with these symbols, the error as well, and this is the t. Already make the difference between that the true error and relative true error. Don't make a confuse. Look at the symbols. The true error will be the capital E, and the relative true error will be, so it is Roman E. Okay, the small letters of Roman E. Okay, so E true values equal into the true error divided by the true value. Okay, so true error just now you got based on the formula and divided by the true value, the what you obtained from that the calculation. Okay, now take a look at this example. All right, so I can show you. All right, so the steps how you can find the relative true error. Okay, so first of all, what you'll need to do, we use the same example of the example 2. Okay, so usually we know that the based on the given function, all right, so which is fx 7 exponential 0.5x at the point when x equal to 2, and the step size with the 0.3. So we know that the true error is, how much is that is now? It's a negative 0.78, sorry, 0.750606, isn't it? Okay, all right. So we know that the through error. So now we're going to find out that the relative through error. Okay, so relative through error. Okay, so you just use a formula. All right. So as we know that the relative through error is the symbol is given into t. All right. So this is will be the through error over the true value. So which means you can easily find a solution. So which is a minus, substitute the value 750606. Okay, and this is like easily you can capture from that your previous calculation. And the true value, as you know just now, is for the function is a 9.5 13986. Okay, if you just find that the solution, you use the calculator, so you get the value which is minus 0.0 minus 0.07 8895. Okay, so if you just leave it in this form is also acceptable, but usually in practice in the numerical methods, so we have to give that value in terms of percentage. Okay, so as in the percentage, so we just multiply the 0.078895 times with 100. That's it. Okay, so they give you the solution, which means the relative through error will be is minus 7.8895. You just give the 4 decimals places. All right, for to show that accuracies. Okay, so this is way how we need to show that the your calculation. Sometimes they will ask you that absolute relative through error. So then it's absolute, it's just very easy. Just put that the absolute modulo signs. Okay, the absolute relative through error. So you can calculate it just when it just put the modulus. So the negative will be assumed to be positive. So 7.8895. So also right. Okay, so that is when it comes to the absolute errors. Okay, so usually in mathematical method, all right, in best practice we use that absolute maximum error or absolute error. Okay, so that is here that the positive value. Okay, just for your knowledge. All right, if the question just mentioned relative through error, so there has to be in that in the way, or absolute through errors, then you have to give that the positive side of the error. It's just the same, just only the difference. All right, that is show the difference. Okay. All right, now we continue. All right, approximate error. Okay, so when you come to approximate errors, why we need to use the approximate error? Okay, so the approximate error is only can be used when that exact value or the true value which is not to be given in our solution or any of the problems. Okay, so and also like when we find out that the exact value is difficult to obtain. Okay, all right. So in that situations, what will happen? The approximate error is defined as that the difference between the present approximation, all right, the present approximation and the previous approximation. The previous approximation also we call that the calculation. We calculate initial value, okay, or the value we calculate before. The present also some books they refer to as a current approximation. Okay, all right. So true value also remember that some books they refer to as a exact value. Okay, remember that. Okay, all right. So the formula is in order to calculate, we can easily we can calculate the approximate value, which is the given the capital E, and the A stands for the approximation. All right. So the error approximation is we can easily calculate based on that the present approximation or the current approximation minus the previous approximation. Okay, the previous approximation. That means that the value we just right before you find out that the current one. Okay, so based on these two, the difference will be that the approximate error. Okay, so let's see some example how they calculate that approximate error so that you get some broad pictures when you calculate this type of the problems. Okay, I'm using the same example, all right, the previous example. Okay, so the fx equal to 7 exponential 0.5x at the point when x equal to 2. All right, so now we're going to determine the following cases. For the case when the step size or the h value, as I said, the step size, which is 0.3, and then we use the step size, which is 0.15. Okay, if we compare to two step size, this is smaller. All right, so by that these are more accurate solutions compared to this. And then, but however, we need to find that the approximate error when it changed between from 0.3 to 0.15. So the difference is the 0.15. Okay, all right, now it's very easy to calculate. All right, first what you need to do, you need to find out that that approximation function, which is the first order forward finite difference. All right, uses formula that is a standard approximate value and very common in use in the numerical method. And then you just plug those value into the formula. All right, so in the given the finite difference formula, so you just plug the functions according to it. So this is x plus h, so which means is 2.3 times the 0.5, and you get the answers, the true value. Okay, and then when it's a step size of 0.3, so you get this value. And then for the step size for the 0.15, you're going to do the same way. So we just plug those value into the approximate function, finite difference function. So, and this is step size now become a 0.15, and remember that the h is also, all right, 0.15 plus 2, it become a 2.15. Okay, and then you find the answers, you yield 9.879850. Okay, now this is obviously your current or your present approximation. Okay, this is your current or estimation or your present approximation function value. Okay, present value, and this is your previous. I'm thinking you can use that CV because current, and this is your PV, your previous value. Okay, now you can use the formula. All right, the approximate error function. You can get that value, which is present approximation minus the previous approximation. So present also current, as I said earlier, current approximation, and you just substitute this value and you get minus 0.38472. So this is the difference between these two figures, two approximations. Okay. All right. Now next we're going to find that the relative approximate error. Okay. So as I said earlier, the relative approximate value, it could be in the percentage. Usually it will be in the percentage. All right. The formula as is actually the ratio between the approximate error and the present approximation. So we can express that relative approximation error, which is that the small capital Roman E, and is the A is stand for the approximation. Okay. So is how you need to denote this value. Okay, for just don't confuse with that. All right, this is like the error E here is for that the approximate error. So when you come to that the relative approximate error, that will be that small capital E. Okay, so Roman E, sorry. So now the formula is the approximate error over the present approximation. So in other words, we can say that we use the formula, the approximate error, as we know that this is a present approximation minus the previous approximation. So the over the present approximation. You also can go in that way. Okay. So once you just find out this, and then you keep that, and then you just write that the present approximation, and you will get that the value. Okay. All right. Now take a look at this example, the same example I used, so that you don't get confused. All right. So let's take a look. We're going to look for that the relative approximate error. So as we know, the formula is that exponential A. E error of A, and this is the approximate error over present error. We know that that approximate error is minus 0.384742 over 9.879850, and they give you this answer. Okay, so this is your relative approximate error. So as I said earlier, this usually will be given in the percentage forms. So what you need to do, you just multiply the relative approximate error with the 100%, and you will get that minus 3.8942%. So you just leave your 4 decimal places, that should be fine. Okay, or 5 significant places, it should be okay. Okay, so this is how you're going to calculate your relative approximate error. Okay, any questions so far? This is it clear? Is it clear, guys?
Yes, doctor.
Okay. All right. So again, when we consider like absolute relative approximate error, so as I said earlier, when they consider that absolute, so we just read as the positive value, which is we just take out that value, which is they give you as 3.8765%. Okay. So always remember, when it comes to absolute, we have to denote that the modulo sign. All right, remember. All right. Okay, so the tolerance error, the absolute relative error has to be less than or equal 0.5 10 power of 2 minus m percentage. So this is like the theorems that what we usually use in order to determine the significant digit required so that the stopping criteria is fulfilled. Okay, take a look at this example. All right, so now remember that the absolute relative error has to be in the percentage. Okay, I have to look into it. Okay, it has to be in the percentage. All right, so how you got every section. So usually when you just look for that H size, H is a step size, as I said earlier. So at the beginning, when the H step size is 0.3, so you're unable to find any of that the error. Okay, you cannot find any of that the relative error out of it. So it means, so it's the first point, so you're unable to determine all that the relative error. Okay, or absolute relative error. Okay, so this is not available. For the when the step size is just reduced to 0.15, so when you substitute in that your approximation equation, so you get 9.87. So how you get this value is you take the current value, or you can take the present value. You also can say that the present value or current value minus with that your previous value, okay, and divided by the present value, and you will get that the absolute relative error. Okay, this is absolute error without percentage. Okay, without percentage. So when you multiply with the percentage, and you will get that this value, which is 3.8942. So likewise this. So when at the point 0.1, so you subtract the value into the approximation function. So you get the 9.755850, and you subtract with the previous value, so 9.879850, and divided by the present value. which is 9.755850. So you will get that the absolute relative error. Okay, and then if you convert into the percentage, then you will get that 1.2710. Okay, yeah, and then say now we're going to determine that m value. Okay, we're going to determine the m value. So which means, so as I said earlier, so at the point, look at that the theorems. Yeah. So at the point the theorem when m equal to 1, all right. So this will be represents how many percent? If it is m is 1, is 2 minus 1 is a 10, so 0.5, so you get a 5%. So likewise, when m is equal to 2, so you get a 0.5%. If it is m3, so you get 0.05%. So now you need to determine whether that your value you obtain here, you have to look at that based on the theorem in order to determine the m value. Say look at that when the 0.15 step size, and you get that the absolute relative error is a 3.942. Okay, so if you compare to this, is it fulfill the condition? Is it the 3.8945 less than 5? Yes, it is. And if you compare to when m2, so which is not, it's not a fulfill the condition. And for the m3, it's not also, it's fulfill the condition. That means if the m is satisfied equal to 1. All right. So please correct that in your updated one. Okay, don't look at that the old one. Okay, look at the updated slide. Okay, then some human error. Okay, all right. So now the m you can easily determine by 1. All right. Likewise, you had to do that the remaining calculation still follow this condition, or else you can use the log function. Okay, so you can use the log function, or so this is a method 1. Okay, so method 2 you can carry out by using a natural logarithm or just the ln function. So you can use a 3.8942 equal to or less than or equal to 0.5 times 2 minus m. Okay, so it is in the percentage and this is in the percentage, so then easily you can determine this value. So 8942 over 0.5, and this will be 10 power of 2 minus m. Right, you continue a solution here. So once you just simplify it, so you just use that the log function, or you use that ln function. Okay, so either one of these you can use in order to determine that m value. Okay, so the lowest value, all right, will be take into that account in order to say like 1.3 something like that, or 1.4. So you take that the lowest value where this fulfill the conditions. All right, you take the m equal to 1. If it is 2.1, so take it as a 2. If it's 2.9, still you need to take it as a 2. Okay. So likewise, we have to do for every iteration in order to get that the m value. Okay, so make sure you just do as a homeworks. All right, you'll find out. I think I just give some example as well for self-test. So please go through it. Okay, so this is self-test. You had to do it your own. Okay, and then practice it. All right. Any questions of this?
Yes.
Yeah, can you speak louder? I can't hear you.
Can you hear me now?
Yeah. Can you? Okay, who's that actually? Can you please tell your name?
Zino.
Okay, Zimo. What is that? Zimo?
Does M necessary to be positive?
Excuse me, hello?
Does M necessary to be positive?
Yeah, it is same as positive values. Okay, so when usually they determine that Hamlet, they will tell you the significant place, a significant digit. The M is an natural values. It will tell you that the number of significant places needed in order to the stopping criteria fulfilled.
Oh.
Okay.
Will doctor give us the answer for self-test or discuss with us?
Self-test is for your own works. So we will discuss during our tutorial times.
Oh, okay.
Okay, so do it first, and then you do it in the, we can discuss during our tutorial next week. Okay.
Okay, thank you, doctor.
All right. Okay, any other question, guys? Any other questions? Hello.
Hello, doctor.
Yep.
Yeah. Afiq is talking now.
Okay,
So
Hafiz.
for the
Yeah.
Afiq, doctor.
Oh yes, Afiq. Go ahead.
So for the method 2, isn't that we have to use the absolute value one, not the percent one?
Oh, you just use the percent one, the percentage here.
Okay.
Okay, we convert it because we have to make a balance both sides. Okay, so this is, it will be in the percentage. This is like the absolute relative error. So you have to make it equal when we make it equal with the theorems. So since the theorems are already in the percentage, so you need to make the absolute relative error as well. It must be in the percentage. Okay.
Okay, doctor. Thank you.
Clear? All right. Okay, guys.
Hello, doctor. I'm Ken.
Yeah.
I have a question.
Yeah, sure.
The method 1, is it possible to have like 50% and 500%? Is it possible to compare with those higher
Depends.
percentage?
Yeah, can depends on the solution that you obtain, the approximation error, the one you obtain from your solutions.
Oh, so doctor, that means that, so if we have 50% or 500%, that means that the M can be 0 or -1, -2, right?
Could you please repeat your question?
Also, so as you can see from the screen, the method 1, when M equal to 1, we have a 5%. So if we are
Okay.
comparing with,
So this is just comparisons, like when we just say the M is 1, so one significant digit in order to satisfy that criteria. So this will tell you that percentage errors, how much percentage is. So, and then we need to compare with that the percentage error or the absolute relative error, the what we obtain from our calculations. So every time the iteration process is repeated and they give you answers for the different step size, so they will tell you that error between the two step size. Okay, but usually there will be very less. Okay, so when we run the simulation in the computer, so at the certain mass size, the stopping criteria will be, we have to determine. Normally, in practice, we will determine the stopping criteria, how much we need. Sometimes this will be 10 power of -5, or some for more accurate solution, we go for higher, which 10 power of -16 or -20. It depends on our control. It's all under our control. So of course, we usually look for the desired solution. So regardless, whatever the stopping criteria is, so once the stopping our desired solution, we already know that what we want, so we can adjust the stopping criteria according to our decisions. Okay, so usually in practice, best practice I ask my students to just stop the stopping criteria 10 power -10. So that is more than enough. Okay, so in order to get that the most approximate solutions to compare to the exact solution. Okay, even the scientific reading in scientific world, so we require that standard. Okay, So unless what happened, we set our stopping criteria higher, like -16, -20, or -100. So the computer simulation will be keep continuing until they stop that the many digit of that accuracy. So what will happen? So this it will cost a lot of times, first thing, and also like they are consuming your computationally very high, because the computational complexity is very high. So that means we have to should not carry out all of things. So the time and the computational complexity is very important in order in numerical methods in order to you compute any of the numerical solution. So we have to always remember the cost is very important. Okay, so we have to stop your simulation at the point once that the simulation or the calculation already reached that our desired solution. So we not really required further than that. So like for example, say we just take the example, we're measuring that a weight of say weight of a person. Okay, so we just use that the device, the normal weighing scale. All right, we just weigh that. We know that the person weight is 75 kilos. Okay, but the same times we use that another digital weighing scale, but it's accurate, say it's about like 4 significant places. So they give that the weight about 75.345 and so on. So, okay. So for normal practice, we don't really need that the accurate for that particular case. So that means we can use that the best possible we just use the normal weighing scale. We don't have to use the digital. You don't really require the very precise weighing scale. All right. So likewise, the stopping criteria. So it's all based on our desire where we need to stop the iteration. Okay. If you just set more tolerance error, then you will take the more iteration and you will take that more time. And definitely they will be consuming a lot of time as well as your cost of your calculations. Is it clear, Ko?
Yes, thank you,
All
Doctor. I understand that.